Welcome back to the channel. In our last video, we dove deep into fine-tuning the large language model, especially the Lama 3.2 1 billion parameter model on a single GPU. We implemented everything line by line using PyTorch. In this case, we did not use at all the Hugging Face trainer method, but there was a catch. Even with fine-tuning with just a single sentence, we were hitting around 12 GB of VRAM, and that is strictly too much. In this video, we are tackling that head on. We are going to learn how to slash that VRAM consumption down to less than 2 GB. We are talking about advanced techniques like Low-Rank Adaptation or LoRA and Quantization Aware LoRA, or also known as QLoRA. These methods not only dramatically reduce GPU uses but also improve your model's performance. So if you are ready to optimize your fine-tuning workflow and make it more accessible, let's get started. These are the two sentences which we wanted to fine-tune the Lama model. Just two sentences, nothing crazy. Because before we fine-tune the Lama model on this task, and I asked the question, for example, how does BGXAI help in fault diagnosis? I created this message, I pass it into my tokenizer, and then I pass it to my Lama pipeline. And this is the generated text I get. I don't have information on BGXAI as my knowledge cut up in 1st March. Whatever. So it basically cannot answer. That's what we are getting it. So after fine-tuning, we're able to extract the answer, the correct answer, in fact, that BGXI provide explanation for fault prediction. But at this time, it's just memorizing, and that's our first step. There are some techniques which we can implement to reduce this VRAM utilization to less than, let's say, 2 GB of VRAM utilization. And also some fine improvement on how we can make our model better. So let's talk about the first improvement that we could do. Right now, when we are doing the loss calculation, we are doing it on the entire message, including the system message, the user message, and the message of the assistants. But that's not necessary. We should just calculate the loss on the assistance message, that assistance response. For example, this is our entire message, which consists of the system message, which is added automatically. Then the user's query, that how does BGXI help in fault diagnosis, and finally the response that the assistant should have produced. Right now we are basically doing a causal language modeling on the entire message, but that is not ideal. Why? Because if we train the model on let's say the system query and also the user query, then the model will learn to replicate them as well. But we just want it to behave as a chatbot and answer the question answer the question and not repeat the question. But when we are calculating the loss based on everything before, let's say the user query, for now let's consider the user's query, then we are training it to repeat the user's query, which is not ideal. So ideally we should just calculate loss on this part and ignore all the other prediction when especially we are doing the loss calculation. Let's say how we can do this. So this is going to be a two-step process. We are going to divide our tokenization into two steps. First, we are going to tokenize only the user query, and next the whole question. So let's see. So my query goes like this: how does BGXI help in fault diagnosis? Then I tokenize. So let's see, what is my token? This is going to be basically the input IDs like this. And if I want to see in the text format what the hell is this, then I can just remove this tokenize equal to false. And we see, and because we put here add generation prompt is true, that's why it also added this part. Assistant start header ID, assistant end header ID, so that it will start behaving as an assistant, because this is how the Lama model is trained. All right, we save this in the tokenized query. Now we'll tokenize the full message. Here we have both the question and the assistant's response. Now we'll do the exact same thing, this thing here, and we call it the tokenized full message. So the tokenized full message is definitely going to be longer because it also contains the query. Before, what we are using is this tokenized full message was our label, basically just once shifted, but you get, we are not changing anything on that. But now we'll change in PyTorch. Whenever there is -100 in the label, basically when you are calculating the cross entropy between the prediction and the label, whenever in the label there is minus 100, it ignores that. That is the default behavior of PyTorch loss function, especially the cross entropy loss function. So we are going to leverage that. We are going to put minus 100 for all the tokens that we want to ignore. In this case, for all this part, all the part covering this particular text. And this particular, the tokens covering all this part are already present in the tokenized query. So first we'll copy the full message as a label, and now we'll replace. Now we'll replace saying fill it up with minus 100 until the length of the tokenized query, which is this one. And in the rest of the tokens, just copy whatever is there in the tokenized full message. Now what you see is all this minus 100 is for the tokens that occupies the system message, the user query. That means we'll not calculate the loss for this one, and we'll only calculate the loss for the tokens that are present for the assistants. To verify this, what we can do is, so now I say that only give me the tokens which are not equal to minus 100, and now I'll decode this. See, now I just get the answer that should be given by the assistants or the chatbot. And yeah, and this is what I should calculate my loss on, not on the entire message. I hope that is clear. And in the next step, we just convert them into PyTorch and send them to CUDA or GPU if you have a GPU, or just CPU if you are using a CPU. And now the same thing. Now nothing changes. It's the same loop that we did before. The only thing is now we are just calculating loss on the assistant's response. Yeah, it can easily generate the answer now. But however, till now we have not reduced any GPU consumption. It's exactly the same as it was before. So now our goal is to reduce this GPU memory consumption. And one of the very important method to do that is something called LoRA, or low-rank adaptation. So let's understand the theory a little bit. That what this LoRA does. Usually when we fine-tune, we fine-tune the weight. So in the fully connected layer, the weight is usually a rectangular matrix. Let's say D cross D or D cross R, something like that. And we usually fine-tune this. In this case, let's say the blue one is the weight we should have fine-tuned when you're doing the full fine-tuning. But that's not necessary. It's turned out that when you are fine-tuning a large language model, which is already very general, which is trained on a lot of dataset, and when you're fine-tuning it on a smaller dataset, we just want it to align to that. We don't want all the parameters to change. It turns out that we can change very little parameter and we can align our model to that particular domain. So for that, this low rank adaptation came. So what that is the adaptation part, that we want to adapt it to the new domain. And what is low rank here? So it says that instead of training one large matrix of W, we can train two smaller matrices. For example, let's say we'll name them this two smaller matrices A and matrix B. And if we multiply A and B, they will have the same shape as W. But individually, the number of weights they have will be less. And how is that going to be? I'll show you in the next part. So to understand the LoRA, I created one example. For example, let's say this W matrix has 1000 cross 1000. It's a 1000, basically 1000 neuron connecting to another 1000 neuron. So it needs a 1000 cross 1000 weight. Basically 1 million weights we need to update if we want to fine tune this simple neural network. But using LoRA, we can decompose this large matrix into two smaller matrices. Let's say A and B. Okay, and let's say what this A matrix, the shape of A matrix will be, it will be 1000 into a rank. Rank is defined by the user. Let's say 2. In this case, we are taking 2. And for the B matrix, it will be the transpose of it. That means rank cross 1000. So when you multiply A into B, it will be same shape as W. I hope you get it, that whether rank is 2, 3, 4, 5, any number, if we multiply A and B, it is going to have the same shape as W. Just increasing the rank will have more parameters in A and B. I hope you get this. to print this, so here I first print total number of parameter, which is 1 million in my W matrix. But if I use rank 2, I can get the same shape as W by having to train less parameter, which is only 4000. So now you tell me whether you like to prefer to train 1 million parameter or 4000 parameters. So that's what LoRa gives us advantage. And in the end, when we multiply A and B, we get the same shape as W. In this case, I call it W LoRa. And we are just using 0.4 percentage of total parameter. So this is crazy. And that's why this LoRa method got so popular in both in language domain and also in the generative images domain. So that is the idea about LoRa. But how we can do this layer-wise layer in our large language model? For that, this parameter efficient fine tuning comes into play. First, I'll import some necessary library. I'll clear my GPU and I'll import the Lama model freshly so that I don't have any GPU cache laying around. And I get like 2300 MB after importing my model. And let's see different layers in our model, because all the large language model have attention in them. So they have a query, key and value pair. And this is what you see. You can do the parameter in model.named parameter. This basically gives you a Python generator and you can loop through it. So parameter 0 gives the name and you can type like the data type. Parameter 1 gives the weights of that one. You can write D type to get what data type they are in. And require grad, say that whether they are trainable or not. If requires grad is true, that means we are calculating the backpropagation for that weights, otherwise we are not. If we print this just after loading the model, we see that require grad is true for everything. And everything, all the weights are in BF float 16. Yeah. And now we'll do this. We'll attach this LoRa layer, this LoRa weights on different layers. It's very simple to do. This library makes it very useful. The PEFT library. It's now integrated very well into the Hugging Face ecosystem. So we get the LoRa config and there we specify. So this R or rank stands for the what is the intermediate rank you want. For example, here you can have rank 2, 8. It's good to have in multiples of 2. So basically increasing this one will let you train more parameters. And right now we are keeping it to be 16. This LoRa alpha is a parameter that scales the LoRa, because in the end what happens, you combine the W matrix and the A into B matrix, you add them together. So when you're adding the A into B matrix with the original weight, which is frozen, what scale you are multiplying it? That's what this LoRa alpha regards as. Then we specify the target modules for which we want to attach this LoRa layer. And usually it's suggested that you should only attach to attention layers. We specify the task type, whether we want to use dropout in this LoRa layers just to avoid overfitting. And yeah, that's about it. And after that, what we do, we call this get PEFT model or get parameter efficient fine-tuned model. We pass in our model the model that we imported and this configuration that we created, and it will give us this model. Now this model will not be the same as it was before. Now it will be a PEFT model. See, now it changed. Before it was just the Lama for causal LM, but now it changed. It became PEFT model for causal LM. And also there are like you'll see here. See, now there are LoRa A and LoRa B. These are the A-B matrix that we are talking about. So what happens is this LoRa, when this LoRa weights are attached, they are initially in float 32, but we don't need float 32. We can degrade them to float 16 to save some VRAM in the future. So that's what I'm doing manually, that I am going and I'm checking if there is LoRA in the name of the parameter, then convert that to float 16. Now you see, this is all the parameters I have, or almost 1 billion. And right now I have only 0.9. That means less than 1% of total weights I'm going to train. So that gonna save a lot of VRAM for me. Now if I run this, you see these are the LoRa weights, by the way, LoRa A, LoRa B, and they are in BF16. And for them only the required grad is true, but for all other layers, the required grad is false. That means we are not gonna train them. We're gonna keep them frozen, and we are only gonna train the LoRa layers. Now there is nothing to change. It's going to be exactly same as what we did before. We're going to create a query, a full message, because we don't want to calculate loss on the query itself. We just want to calculate loss on the response of the assistant. Just what we did at the starting of this video. We create them as a PyTorch tensor and pass them to the GPU. And now it's time to run. One great thing happened here, that now my reserved memory went from 12 GB to let's say about 3 GB. About around 3 GB of VRAM, I can fine tune my entire data. Let's see if it works well or not. Yeah, it in fact does give the same result even with the LoRa training, which drastically reduced our GPU utilization. We can go even one step forward, where we can use QLoRA. QLoRA stands for quantized LoRA. The LoRa part I already explained what is it. Now let's explain what is quantization. Quantization is nothing but converting a higher memory format to a lower memory format. And to use this quantization, there is a library called Bits and Bytes. It was originally created by Facebook AI Research, and now it is well integrated into the Hugging Face ecosystem as well. So we can use this very easily. We need to import this library. And if you haven't installed it, you have to install it just by calling pip install. Let me restart my kernel so all my cache are deleted, and we can start afresh to see how much GPU utilization we are getting now. All right. So to explain what is this quantization and everything, let me create a tensor. So I create a tensor in float 32 format. It's of shape 10,000 cross 10,000. All right. After creating this, I'll print the GPU utilization to see how much GPU space it consumes. And after that, I'm gonna convert it into a 4-bit format. I'm not going deep into how this conversion happens. There are a lot of video you can find on internet to show that how this conversion happens. But on a bigger scale, what it basically does, it for each weight matrix, it calculates the maximum, minimum. It gets the maximum value, the minimum value, and it scales it down to an integer format. There is some loss in this. So once you convert it to 4-bit format, when you go back to the let's say you're going from 32-bit format to a integer format, and then when you go back to the from integer format to the float 32, you lost something. You don't get the exact value. I'll show that in just now. So for now, let's say we quantize it to 4-bit, and this will be, I call the BNB, the bits and bytes dot functional dot quantize into 4-bit. So you can pass it any weights and it will quantize it. So let's see. Before, my GPU utilization was 384 MB, and after quantization, it becomes just 53 MB. So when I went from 32 float format to 4-bit, I reduced, let's say, 8 times. Almost 8 times my GPU utilization, which is crazy. Now let's take this quantized vector and take it and make it back to the original format. We'll see whether that's same or not. So this was my original tensor. This is my quantized tensor. You see they are quantized into int format. Basically they are in unsigned integer 8. One question you might be having in your mind, that if it is int 8, then why we are calling it quantize into 4-bit? Because the format it is in the format the weights are in, it is unsigned integer 8. Then why we are calling it 4-bit integer? So to answer to that is in the bits and bytes library, they save 2 numbers in the memory of one unsigned integer 8. That means whatever memory one unsigned integer 8 number would have consumed, they put 2 numbers in there. So for that they call it like a 4-bit quantization. But yeah, that goes more in the theoretical way, but I want to show that how we can apply that. This is my the number I created, 100 cross 100 in float 32. Then I quantize it. This is my quantized tensor, and then I dequantize that float 32 version. All right. So let's see. So this was my original tensor, and this is after quantization. You see, they are not the same. There is a little error, but however, more or less, the sign remains the same for some integer, for some numbers. For example, this one minus 2.59 minus 2.59. They're pretty accurate. 1.89. This one. So yeah, there is some loss in someone, but more or less they have the same structure. So this is the loss I am talking about. Whenever we are doing quantization, we lost some information, but we also gain GPU VRAM. So for example, if you could not fine tune at all, it is better that with little loss, you can fine tune a model in your GPU. So that is the trade-off that we are accepting. And also another interesting part is when I'm generating this 100 cross 100 tensor, what I did is I created a histogram out of them. Basically 10,000 numbers I have, I just put them in the histogram, and this is how it looks in float 32. And when I convert it to, like, say, the 4-bit quantization, this is how it looks in the histogram of all the numbers. And after I dequantize, this is how it looks. So here you see the loss, exactly where the loss happened. So what is happening? You see there is nothing close to zero. All of the weights are basically zero. Why that happens? Because let's say we have a lot of numbers basically close to zero. For example, there is a number 0.12 or minus 0.25. Those all numbers after quantization get squeezed to become zero. And when you dequantize from zero, they are all zero. So you lose that information. That's why all the numbers close to zero, they are squeezed into the zero. And that's why you see a very big spike in the zero value, and there are nothing. This all we understand. But one caveat here is when you convert your weights into, when you quantize your weight, this quantization is not differentiable. So you cannot back propagate after you quantize. That's why the researcher come up with this idea that for most of, when we, let's say we have the Lama 1 billion parameter weight, the original weight will keep them in quantized format. We won't do the back propagation through them. But what we will do is, so this is the Lama weights, and these are all the attention layer, and they are all in unsigned integer 8 or the 4-bit quantization, as you can see. This will remain frozen. They will not be trained. However, we'll add a LoRA blocks to them. That LoRA block we saw just before, we'll add them, and they will be trainable. They will be in, let's say, float 16 or float 32, depending upon your use case, and we'll only train them during the backpropagation. So this is a very clever way where we can even reduce our VRAM utilization even further. We can fine tune a big model on a consumer grade GPU. So now let's go ahead and do it now. So one important part is how we convert our the Lama model's weights into 4-bit format. And here it comes. From the bits and bytes library, we import this bits and bytes config. Here you can write load in 4-bit equal to true. And what is the quant type you want to use? This is called normal float 4. What is going to be your compute type? It can be either float 16 or float 32, depending upon your use case. Whether you want to do double quantization to even reduce, it also reduces, I think, by 5 to 15% further your GPU utilization if you do double quant, but also it reduces a little bit of accuracy. And then all you have to do is, when you're importing the model, you have to write quantization config and pass this BNB config in there, and that's it. And after the import, now it takes only 1 GB of your GPU of your VRAM. Before it used to take 2.3 GB of your VRAM, where we are reducing our GPU utilization by more than half. So that's pretty cool. Now we'll apply the LoRA. This is the same thing that we did before. And here we see that only the LoRA layers are being trained. That means require grad is true here, and all the quantized layers are not being trained. For example, this one, let's say this layer is been quantized into 4-bit. Then why it says the torch type is BF float? This is because when we do the forward pass or backward pass, it converts the weights which are saved in the 4-bit format to float 16 during the multiplication. That's why it says the computation happens in float 16, but the storage happens Like when it's stored in the 4-bit format. Now the same thing will create our training data. Training data is fairly simple, that the question that we have been using. See, after that we train our model, and you see that the maximum GPU utilization has dropped to around 1.3 or 1.4 GB, which was before for the same input, which was before, let's say 11 GB, we bring it down to less than 1.5 GB, which is pretty crazy. And let's see whether it was able to generate the right answer or not. Yes, the answer is still accurate. However, the GPU, the VRAM consumption has decreased by 10 times by using these advanced techniques. So yeah, that was all about this video. In the upcoming video, I'll show you how you can fine tune on a dataset, because right now it's trained it on a single sentence. How we can do this on a dataset by using all this, by especially using QLoRA, quantized LoRA. If you like this video, subscribe to the channel, give it a like as well. And until next time, stay curious.